Welcome to Three Devs and a Maybe. Now introducing your show hosts, Michael Budd, Fraser Hart, Lewis Keynes, and Ed Mann.
Hello and welcome to another episode of Three Devs and a Maybe. My name's Ed Mann, and today we're lucky to be joined yet again by Scott Wlaschin. How you doing, Scott?
Hi, thanks for having me on.
Well, thank you again for coming on, man. I really appreciate it.
It's great to be here.
So last episode we did a massive talk about your DDD book, which I should now say is in print form, which is awesome news. I'm sure you're really happy with that.
Yeah, it's finally out in print. And if you go to my website, you can see all the places you can buy. It's got buttons to take you straight to various places, so that's good.
Is there something about having a physical book? There's something still kind of nice about that.
Yeah, there's something about physical books are great. It's nice to have something instead of a Kindle. You can put post-it notes in, and you can do various other things.
One thing that we were going to try and discuss that episode, but because we were talking so much about the DDD stuff, is the talk that you gave at NDC London in early January, The Power of Composition, which is just a great name for a talk. Now that it's available kind of in video form, and I was able to actually get to watch it, and I was wondering maybe if you could introduce the talk and what actually it covers to the audience.
Sure. It was the reason I did the talk is because if you're a functional programmer or you're new to functional programming, you hear about composition all the time. Composition this, composition that, and it's hard to explain. Often people don't really explain what they mean by that and why it's so great and why it's so fantastic. So the goal of this talk was really to explain what is composition and why it is so important. And once you have a system which is designed around composition, which is one of the kind of strong points about functional programming, if everything's designed for composition, then you get a lot of benefits in terms of how you build programs and how you reuse pieces of code. And it's kind of really obvious, but there are certain things in order to get composition to work. There are certain things you need to do and certain little things you need to look out for. So that's the kind of stuff I talk about in the talk.
Obviously, it's kind of, taking it from a functional mindset, but can this be applied, to the OO world when we consider a composition there, or is there subtle differences?
It can be, but one of the things, there's a couple of problems in the OO world, which is that for composition to work, you need to have certain things like no side effects, and that means no mutability. And that doesn't, object-oriented systems tend to have a lot of mutable state everywhere. You can sort of design OO systems not to be that way, but most, mainstream languages don't really help that. And just in terms of working as everything as an input, the pipeline model for composition, you have an input and output, and you glue these pipes together. Object-oriented models don't work that way in general. You don't have inputs and outputs. You have requests and responses, and you have these big objects that can do many different things, and it's hard to glue them together without some extra plumbing. And one of the things about a system designed for composition is you can glue them together without any extra plumbing. You can just literally take two things and stick them together.
Absolutely, yeah. And it's kind of like you compose based on objects, obviously in the OO world, which has like on it a boatload of methods attached to it already, whereas in a functional world, it is just a function.
Yeah, and this is where keeping the data separate from the behavior, it obviously in the OO world, the whole point is the behavior and the data are kind of linked together in one single object. And in a functional paradigm, the data and the things that act on the data are completely separate. And so it's not at all object-oriented, but it does mean that you can glue things together. Because they're separate, the data and the functions can be composed independently. And you only have to worry about one thing when you're gluing together functions, as opposed to trying to compose different kinds of objects. It just doesn't make sense. Often you end up with all sorts of complications when you try to do that.
And then, you mentioned function composition, but then obviously the fact that the separation of the data and the actual action, you also get type composition.
Yes, I mean, most functional languages have something which is called algebraic type system. And I like to call that a composable type system, because the big benefit is you can glue types together, because types are just data. Their types in a functional world are much more like sets than like objects. So it's just data, a set of data, or a set of things that you can use in functions, and so you can add them together. You can have a kind of Cartesian product of those things, and that's like what we call a product type. You can kind of union them together. We call those a union type or a sum type. And you can actually build from those kind of basic things. You can use the same principle of composition, building bigger and bigger things from small components. You can build really sophisticated types that can do all sorts of clever things. And again, because there's no intermediate glue needed, you can just literally glue types together. It's a lot easier to do. In the functional world, or certainly in the typed functional world, we have lots and lots of types. We tend to use hundreds and hundreds of types, while in a OO world, we tend not to create so many classes because it's kind of heavy and unwieldy.
You mentioned at the beginning of the talk a type. Well, actually, I think it's hilarious. At the beginning, you obviously say, what do you know about inheritance and all this kind of stuff? You're better off trying to keep that our way when you're trying to learn these functional concepts and composition in this regard. But it was interesting because obviously you mentioned like with types and everything, how having like, say, an object is a class and types like that, but they're very different to the types that you will get, which are just essentially just kind of sets.
Yeah, I think it's one of the things, and I mean, I try and do that. I did this thing, as you say at the beginning of the talk, where I say, if you want to learn functional programming as a beginner, you need to forget everything you know, because it's just, if you try and say, well, how do I do a class? How do I do a loop? How do I do this? So it just doesn't, you're trying to think in the wrong way. It's better to approach the problem with a beginner's mind and like, how do I even do anything? And then the problems are the same. It's like, well, rather than saying, how do I do the strategy pattern, or how do I iterate over a loop, iterate over a collection? You say, well, how do I parameterize the behavior of something? Or how do I do an action for each element of a collection? Those things are the same. That's a design problem. But the implementation technique is very different in the functional paradigm and the OO paradigm. So it's really important to forget about implementation and focus on the problems. I mean, like I say, both paradigms address the same kinds of problems, but in very, very different ways. And I've seen people trying to bring OO paradigms to functional programming, and it's just painful because they get very frustrated. Like, why can't you even do this?
So it's a paradigm shift as opposed to just a language shift. If I'm moving from, say, Python to Ruby, I'm very much in the same, OO mutable paradigm that I can it's just syntax change. Whereas, this is a complete philosophy change. It'd be interesting to get your opinion on, because I suppose, there's the idea then that, people get confused when going to functional languages. They just want to kind of, all right, how do I do for loops? How do I do side effects and stuff? And, you have languages such as like Scala, and Scala kind of allows you to write things. It's the best of both worlds in some regard. Like, it allows you to write pretty much Java code, and then you're able to go completely into the typed functional code. Do you find that those languages, I mean, in some regard, maybe F# as well, with certain things it can do with side effects, do you find that confuses people too much? Like, that's the confusion point?
Yes. Yeah, I think I tend to like languages which have strong opinions about the right way. I mean, I like Python over Ruby, for example, because Python tends to be more opinionated. And it's true that basically most mainstream languages are really the same paradigm. I mean, if you know Ruby, you know Python. If you know C#, you pretty much know Java. Obviously you need to know the libraries and stuff, but the concepts are going to be very familiar. Going to a functional paradigm is going to completely hurt your head. So for learning, it's an interesting thing. F# is very, very it's very functional. It does have some object-oriented features. I think Scala takes it too far in terms of the kitchen sink. You can really do some very bizarre stuff on the functional side, and you can do some, classic OO stuff. And I think you end up with a mishmash of paradigms in your code. And it means that anyone who's reading your code has to potentially understand every possible way of doing something. If I'm, and F# isn't that bad. I think if you look at, a language which isn't a very opinionated language, you may not understand the code, but once you understand how the language works, you're going to understand there aren't too many different ways of doing something. And so it doesn't make it easy to maintain the code. Obviously, there's the barrier of understanding the code in the first place, but people tend not to do things in too many different weird ways. And I think kitchen sink languages do worry me, because in terms of maintainability, if you have a large project which lasts a long time, the code just gets to be a real mess. It's really hard to enforce a certain I mean, I think in general, this is the thing, constraints are good. In general, the more constraints you have, people always look for freedom, and I think constraints are good. So the less things you can do, it's often better for a readability point of view, from a maintainability point of view. Having a limited set of things that are done really well, I actually think that makes for a good programming language.
You know, like a language such as Scala, you know, you can see why they decided to do it. You know, it's like the transition period, so you're able to get people to start to use the language. But the trouble is now you almost need that separation of a completely different looking syntax, completely different paradigm shift in its entirety, because all you'll do is to try and see shapes and similar patterns that you already know in that. You know, you need to completely separate yourself. And if you have a language that's like a kitchen sink language, you're able to kind of see already things you already know, and it doesn't allow you to take yourself out and kind of apply a completely different paradigm.
Yeah. When you're learning, it's easy to fall back on your old familiar habits, and it's a tension, because sometimes, I mean, like Haskell, where you really are thrown in the deep end and you have no choice but to do functional techniques. You know, you can't even say hello world until you've had, you know, a month's worth of, hello. In the Haskell books, hello world is like in the 7th chapter of the book. You know, you have to understand monads before you can say hello world. And I mean, I understand why they do that, but that might be a little bit too deep. I think languages which are halfway, OCaml and F#, I think are a good compromise. You can do mutable state there. You can fall back on bad habits, but the language makes it really hard to do that. I mean, for example, in F#, if you want to have a mutable, value, you have to use the mutable keyword. So every time you want something mutable, you have to say mutable this, mutable that. It makes it, you can do it, but it kind of looks really ugly.
And it's explicitly saying this is something you should be looking out for. You know, there's a reason why this is different.
Yeah, exactly. So it just makes it just the bad code kind of looks ugly, and I think rather than forbidding bad code altogether, just allow it, but make it look kind of really ugly. It's the same thing with the object-oriented features in F#, which is very useful if you want to be compatible with C# or all the .NET libraries, which is great. But the object-oriented features tend to look a lot uglier in F# than the functional features. And I think that's good. It kind of discourages you from doing that unless you really need to.
Yeah, that's a nice way of thinking of it, because it not only explicitly says this is different, and this is, but it also, as you say, this is not syntactically pleasing. It's also saying, well, there's this way looks nicer, so this is drifting you to use the ways that the language is actually trying to intend to do it. Yeah,
exactly. I mean, I just think it's a very interesting one. That one of the problems is, as always, we have almost no evidence on makes for good best practices in language design. We for massive industry, and I do go on about this all the time. We literally know very little about best practices in programming, best practices in language design. It's just very strange that none of the big companies have spent money trying to understand this, because there's so much money involved. But basically, we're making up as we go along, and most of the evidence is sort of anecdotal. It's like, I like it this way. I mean, that's true. I like it this way myself. I like opinionated languages. I like languages with concise syntax. I don't know if there's any evidence that's good, but I like it. So what can I say, really?
Because it does seem to go into two camps, doesn't it? It's either very opinionated or it's very much kitchen sink. And it's, either based on, kind of, you say, like you mentioned Python, and then we will talk about closure and stuff, the BDFLs, there's this kind of, someone's leading the front of what this should be and the yay or nay of what's going in. So their philosophy stays, as opposed to, say, like PHP, which is very much like, we're going to solve anything and everything that at that time is deemed a problem. So it's a very general, the whole concept of a general purpose programming language is always strange to me, because it's kind of like, so it does everything then, but then nothing well. I don't know what your feelings are towards that.
You see, people will just I know a lot of people who love Perl, and Perl is the ultimate kitchen sink language. If there's a way of doing it, like, well, here's 10 different ways of doing it. And I know people who love Perl, and that just fits the way they think, and I personally can't stand it. But who am I to say they're wrong? I mean, like I say, there's no evidence either way. It's just personal preference. But I think if you are learning a language, I think it's very hard to learn functional programming in a language that doesn't make it easy. So if you're trying to learn functional programming, trying to do it in Java, is kind of painful.
And it looks ugly as well, doesn't it?
And it looks ugly. Exactly. I mean, there's a good example. Java is designed to have a nice OO syntax and trying to do functional stuff, and it looks weird because it's not really designed for that. F# and Haskell and stuff, they're designed to do functional stuff, and so the whole syntax is built around that.
Absolutely. And it's like, with composition, actually, as a subject matter there, you look at composition in, say, languages like Java, and you have to read these calls, that you're making, composing together, read them inside out, and, nested function call, confusion and things like that. Whereas, in languages such as F#, it's like that's a first-class problem that we're going to have like piping operators for.
Yeah, so this comes back to the language design. If you're going to have composition, you need everything to have one input and one output. Now, functional languages, purely by coincidence, have this thing called currying, where every function is a function with one input and one output. So composition is really easy. It's which came first, but it certainly means that you can compose any two functions together because of that thing. If you're trying to compose different kinds of functions together in other languages, you have to artificially do currying and partial application. It's not a natural principle. So I mean, a lot of the I mean, I wouldn't say that functional languages were designed around composition because they came from, originally they came from a sort of different place. But everything you need to make composition easy, functional languages have. Like I say, the lack of side effects, the lack of not needing to do any extra glue or intermediate stuff in order to compose things together. It makes it's super easy to do composition. So that's why it's become the sort of the dominant paradigm in functional programming.
One thing you're very good at is the analogies, and you did some very great analogies in this talk, kind of comparing composition to how Lego, Brio, and Unix. And I really enjoyed the three main points that you make, that all pieces are designed to be connected. You can connect two pieces together and get another piece that can still be connected and reusable in different contexts. And I think that kind of analogy that you did there really, for me, helps click. And it does kind of show in all these different things how good composition can be and kind of where, it's applicable.
Yeah, I mean, the Lego is the classic example, but I mean, it's amazing how much you can actually learn from looking at why Lego works. Why is Lego so popular? I mean, yes, it's because every piece fits with every other piece. Well, it's obvious that you should design software that way, but in most of code, especially in OO, we don't really design the pieces to be fit.
We've got adapters and all this kind of stuff, and they're all
exactly bespoke. We need to have special adapters. But if you build, if you're sticking two Lego pieces together, you don't need a special Lego adapter. You can just literally, they all have exactly the same kind of interface. You can just literally take any two pieces and stick them together. You don't need, and because you don't need to build special adapters, it makes life a lot easier. You can build really big things from a bunch of small parts. And the second thing, which is that if you connect two pieces together, you get another kind of the same kind of thing. So you stick two Lego pieces together, you get another piece, a kind of a bigger piece of Lego, and you can connect that to other pieces of Lego. This thing that, and we see this, I mean, one of the reasons why, in a simple, a simple thing like adding two numbers together, you get another number, so that makes it really easy to add lots and lots of numbers together. We take that sort of for granted in all sorts of areas of our life. And again, we don't really apply that to programming so much. So if you apply it to programming where if you take two pieces together, you glue two things together and you get another thing that can also be glued together, that's a really, really powerful principle. Now, you can sort of do it in OO, but you really have to work at it all the time. It's not like a natural technique. But in functional programming, it really is the natural technique. It's really easy to do that because of the way that the functions work. Functions are designed to be glued together that way.
Yeah, and the connecting two pieces is obviously then the form of abstraction that you can do in a functional language.
That's right. I talk about that in the talk. It's like if you have, I have a little thing where if you have an apple, a function that takes an apple and returns a banana, and you have another function that takes a banana and returns a cherry or something. When you glue them together, the banana part disappears, and now you just have a function that takes an apple and returns a cherry. And so, yeah, the banana, nobody cares about the banana anymore. You now have a bigger function which I can then give to you, and you don't know how it works inside. All you care is the inputs and the outputs. And again, this is the other thing about, if I give you a function that turns an apple into a cherry, in order for me to give that to you as a reusable piece, it must not have any, that has to be the complete input and output. There can't be any side effects. There's no kind of global variables. There's no writing to a database. There's no, doing anything weird, because if I gave you a function and it relied on a database existing or the file system existing or, a global variable existing or something, you wouldn't be able to use that function. That function would not be reusable. But because there's no side effects and because everything's completely explicit, it's like you need to give this thing an apple and it will give you back a cherry. There's no other inputs, and you can be sure that it will work as a sort of standalone piece. And again, that's one of the things about Lego and Brio and so on. They don't have strings attached. Literally, if Lego had lots of little bits of string attached, it would be the string would all get tangled up and you wouldn't be able to do anything, But we tend to write our programs often where there are strings attached, and which means that you can't. It makes reuse very, very hard, because in order to use this function or this class, you have to have access to this other, this database or this file system or this global variable, this other class that you don't, that's implicitly used in the, inside the class. That's like, well, it won't work because this library doesn't exist and all this kind of stuff. So it's really nice if you can not have any dependencies, and that makes, again, it makes the code much more reusable and much more testable and, much more explicit.
And it just means moving those dependencies to the edge, doesn't it? Like bringing them in when they need to be. Like the side effect happens at the end. So you've got this nice piece in the middle that can be easily tested, easily composed. And then you have all the nasty stuff kind of around the edge.
Yes. I mean, obviously you have to have side effects at some point. Otherwise the program's not going to do anything.
You won't get your hello world.
It just, exactly. It's got to, otherwise it just sort of heats the CPU. At some point you want hello world to be printed on the screen. And so there has to be some sort of side effect. But yeah, the goal is you keep that stuff to the edges. You either at the beginning of the function or at the end of the function. The idea is that the core domain is pure, that there's no side effects in the core domain. And so this leads the functional world, obviously, it can be hard to work that way. So this is the whole thing of where things like monads and all this stuff comes in, because how can we represent things that we want to do without actually doing them? So how can we represent an exception, an error, without throwing exception? How can we say that we want something to be async without actually starting a task? How can we say that we want to write to a database without actually writing to the database? So we tend to build special types that represent those actions. Like instead of an exception, we have an error type or a result type that has a success or failure. Instead of literally starting a task, we create an async type that represents something that we want to do. And, people, all this is where the whole thing of using monads and all this stuff comes in, because it's a natural result of trying to design for composition without side effects. And so all these complicated tools that functional programmers have, it's just a result of solving a problem that comes from, trying to keep things pure and trying to keep things without side effects.
But it's interesting, actually, isn't it? Because obviously someone can come along and be very confused. Suppose with the language that we're very used to, all these languages we're used to, side effects is just a first-class thing. Whereas in functional, it's not a first-class thing. Purity is the first-class thing. So when you see an example that you're typically going to say, like the hello world, you need to understand, or at least, you need to realize that, monads are happening, these things are happening. So having kind of, in an F# way, where you do kind of at least allow you to do some stuff that could be side effecty, we're going to make it look ugly, is probably a good thing, because in the Haskell world, as you say, chapter 7, you finally get onto what you want to do, which is the beginning of how you would normally explore a language.
Yeah, I mean, what's interesting is that I'm not. A lot of people are very, very big on purity at all costs, like literally never having any kind of side effect of anything whatsoever. I'm not 100% sold on that. I mean, I think it's nice to have escape hatches for things like logging, and I mean, it's true. Every time you have an escape hatch, that means makes the function less composable. And so the people who are into purity, it's like every time you do something, every time you break it, it means you can't reuse this function, and it's not as composable. On the other hand, I think the composition as a principle, just like most OO people now use dependency injection, I think most developers realize that making your dependencies explicit is really, really useful. I think you can have a kind of happy medium where the important dependencies are very explicit. Like if you're writing to the file system or something, you don't just do that right in the middle of the code. You pass that in as a dependency. But if you just need to, print to the screen because you're trying to debug something, you don't have to put that in a writer monad just for that one thing. You can just bypass that. So that's my take. I guess I'm a little more pragmatic that way. I can understand other people's point of view, but it is nice sometimes to have an escape hatch. But I think the philosophy, it is definitely sort of breaking the purist philosophy of never have a side effect anywhere.
Because, I mean, purity then is something that's very good for, say, testing. And how do you go around like FP kind of functional programming mindset way of testing things? And how does it differ to you from the OO world?
Well, it depends on whether it's pure functions or the edge functions which do I/O. So the pure functions are super easy to test because there's no, all you do is you say, well, a pure function, one of the things is if you give it a certain input, it always has the same output.
Referentially transparent.
Exactly. So that makes it really easy to test. You say, I give you this input and I expect this output, and the testing is trivial, really. I mean, it's not trivial, but it's, and you're guaranteed that you don't have any weird side effects because these are pure functions. In terms of if you do have I/O, there are a couple of different ways. One is the classic thing where you make a mock. So instead of writing to the disk, you write to something in memory or whatever. That's the same kind of thing you would do in OO thing. The nice thing is, again, that all the stuff is going to be very, very explicit. There's no implicit stuff. And the other thing you do, just like any big system, you do integration testing. So if you are working with a database, it's probably good to run the entire system with a database just to make sure it really works. And there's no way around that. I'm a fan of integration testing because there's nothing quite like working with a real system to find problems in your code. And so, and not all problems, obviously not all problems can be solved with a type safe compiler. There are a lot of other problems. There's logic errors. It's the actual business logic. Yeah. You can't envision that.
Yeah,
I mean, infrastructure. What happens if I try and talk to a database and the database is not there? What happens if I try and talk to a web server and the authentication fails? Like that, that's something you need to think about no matter what programming language you're using. Those are fundamental things that you need to think about, and that's something integration testing can help you think about that. I mean, obviously, if you think about it in advance, you can do that too. But integration testing is a great way of finding problems that you haven't thought of.
And what is your testing philosophy? It'd be interesting to maybe delve into that a little bit. Kind of, did you do a TDD kind of approach to designing software, or do you kind of test as you go along?
I don't do TDD. I think TDD has gone a bit. People misinterpret it. I always liked TDD as test-driven design, whereby the best way to design your code is to pretend that you're a user of the code. And so it's like, rather than trying to have a kind of design something thinking about everything you could possibly need, you say, well, I need to do this one thing. What do I actually need from this class? What do I need from this module to get this thing done? And so you're kind of working from the outside in. And so test-driven design is a good way of doing that. But if you're doing functional program with types, you can very much do the same thing with types. It's like, if I give you this type, I expect this other type as an output. And with the strict type checking, you can, by the time you get all the types working, you have pretty high confidence that it's actually going to work even without testing. So you tend not to test things that you might test in other languages. Like, for example, I never do any testing for null. I never do any in F#. It's very rare to do sort of defensive programming. If I have an email address, I never have to check whether it has an @ sign in it because I've defined a type called email address, and that email that's sort of been validated already. And because it's immutable, and because it's validated once, it can never get out of date. It can never become corrupted, and so I never ever have to test for it again. So those kinds of things, you tend to do a lot less defensive programming. So I tend not to test. I would test if there's kind of complicated business logic, I might test for that. But I tend to do a lot less testing in a statically typed functional language than I would do in something like Python. Absolutely. Because in Python, I never really know. And one of the things about Python or any kind of dynamic language is that the tests serve two purposes. Once for one at the design time, but also later on, if I change my code, have I broken all the tests? It's like, have I accidentally passed in a null when I shouldn't have, and in a dynamic language like Python, you're never really sure whether you did accidentally break something when you've refactored it. So you need to run all the tests to make sure, and hope that your test coverage is high enough that you haven't missed something. In a statically typed language like F#, if I refactor something, by the time, typically when you refactor something, you rename something or you change the type or something, you get hundreds of compiler errors, and you just work through those compiler errors, fixing them all up one at a time. And by the time the whole thing compiles again, you have very high confidence that the whole thing works. You tend not to worry that you've accidentally broken something. That's one thing I never have with F#. I very rarely worry that, did I mess this up? Let me rerun the test suite to make sure. That's not a very common worry. Yeah, so that's one less thing. That's a huge kind of weight off. That's one of the reasons I like static typing. Yeah.
That's cool. I suppose, and static typing, would you say different to how Java and C# does static typing? Kind of, the testing there, obviously you probably would have to do more.
Yeah, because first of all, they have nulls. And secondly, because it's a mutability. So just because I've checked that an email address has an @ sign in it, further down in the program, somebody else might have changed it. So I basically don't trust it anymore. So I have to do sort of defensive programming. So you give me an email address, it's like, is it null maybe? Is it still valid? I don't know. One of the reasons, so the mutability gets in the way, the nulls get in the way, the fact that you tend not to create lots and lots of tiny types. So if I'm programming in C# or Java, I probably wouldn't create a special type just to represent an odd line quantity. I'd probably just use an int. But because I use an int, I'm actually allowing myself to have subtle bugs. For example, an odd line quantity probably shouldn't be negative, and it probably shouldn't be 5 billion or whatever it is. Those are bugs. But by using an int, I haven't really thought about those bugs. If I have a special type called odd line quantity, and as part of the constructor, I say that it can't be negative and it can't be more than 100 or something, then I'm never going to have those bugs where it's the wrong, it's out of bounds. But creating a little type like that, F#, that's like, a one-liner. In C# or Java, that's like 20 lines of code.
That is the problem, isn't it? And I mean, you showed in the DDD talks you've done in the DDD book you've written how expressive a type system like, F# can be compared. Obviously, if you're then trying to replicate that in like the very OO languages, it's a lot more code and a lot uglier. So people are less likely to do it as opposed to just saying, I was passing an int then. But like you say, the set of actually what you're thinking of what could actually be provided in there would be much greater than you kind of envision. That's
right. And the other thing, and just going back to my DDD talk, which is that, if you have a special type called order line quantity, you've now got documentation as well. So if I say this thing takes an order line quantity, it's order line quantity times price, I would tend to have special types of that. And so I've got a self-documenting system by using the types. If I just say it's an int times a float, it's not very clear what's going on. They could be anything. And it's very easy to get them mixed up. An int times an int, which is the first int parameter, which is the second int parameter, and so on. Having lots and lots of types not only reduces errors, but also makes for a more self-documenting code base, so that's, kill two birds with one stone.
That's exactly it. And throughout the talk, you did a lot of good examples. You talked about Roman numerals, composition in that regard, FizzBuzz, which was great. And the one real kind of use case you did was using the Suave.io web library, F# one, and how everything is a web part and how you just compose all these things together. It'd be really interesting. Maybe you can explain kind of that philosophy and how it's using its Kalesis composition.
Yeah, Kleisli composition. Yeah, so this is a good example of the different, a completely different philosophy. Most web applications, they have a controller and they have a view model and they have some domain logic or whatever it is. In the functional model, you want to do composition, so you want a pipeline. So something comes in, like a piece of JSON comes in from the outside world, and you want to say, well, if it's a post and it's going to the /update URL or something, I want to do this. So rather than having a controller method which is attached to that particular thing, you want to do it through a pipeline. So how can you? The pipeline needs to be, every piece of the pipeline needs to be reusable and composable. And so how do you do that? Well, the Suave approach is this thing called a web part, and a web part is a function with an HTTP context as an input. And so HTTP context is everything you need to know about the HTTP context, which is the requests, the response, the cookies, the authentication, whatever it is that you need to know. So that's the input to the function, and the output is an optional context. Which means that if you can't deal with it, like for some reason you want to fail or something, it's like, I can't handle this request, you just say, you return nothing instead of something. And then that's basically it. And because of that, you can then glue these things together. So, for example, you might have a get part, a web part called get, and all it does is match the HTTP context with a get request. And you might have another one called post, which matches with the post. Now, if it matches, it succeeds, and if it doesn't match, it fails. So you take that, and then you might have another one which matches certain paths. So you have the update path or something, and if it matches that, it succeeds, and if it doesn't match, it fails. So then you can glue the get part to the path part, and that one will only succeed if it's a get and the path matches update. And then you can pass that to another one which, checks the cookies or whatever it is, and then you can pass that to your domain logic, which basically takes the body of the HTML request and parses the JSON and turns it into a domain object and does all the domain logic. And at the other end, you would have something like a 200 OK part, which just you give it the input and it responds with a 200 OK as the output. So you glue all these things together into a pipeline, and that's your web app. No objects, no controllers.
No if conditions, no conditionals, all composed and easily expandable, which is just the beautiful thing about it.
Exactly. You just stick in new kinds of parts, and a library would provide a set of parts which you can use. So an authentication library would have some authentication parts. You just stick them into your pipeline, and now you've got authentication.
Have you seen this being used in other languages? I mean, maybe more predominantly OO languages, this kind of concept, because the whole web part concept seems very applicable to any kind of web application. Or is it, I suppose, does it need to be kind of a statically typed language to get the full benefits with the fail and all these kind of things?
Yeah, it's hard to do. I mean, you see a little bit with the middleware in the latest version of ASP.NET Core, where you basically do pass these things around, and there's a chain of people who can act on this, but it's not quite. It's always it's a mutable model. So basically, you pass this thing around, and if you want to change it, you pass it down to the next one. But the idea that a function would fail and you would then bypass the rest of the pipeline, that I don't think is in there. I'm not 100% up to date on how the latest ASP.NET works, but it's pretty unusual in an object-oriented model, and that's only really useful for the middleware. You still have the controllers and the views and the so on.
Because it's such a beautiful model. Like when I saw that code, I was just like, this is the beauty of composition. How you can kind of dilute down to just this, very easy to understand, comprehend type definition and use it in so many contexts. I mean, it ticks off all three of those boxes that, you were the analogy boxes you had.
Absolutely. I mean, it's once you start seeing it everywhere, and I think this is one of the really nice things about learning functional programming, is even if you don't actually use it in practice, I think it makes you a better developer, because you start thinking in problems, you start looking at problems in this way. You say, how can I make this problem into something where it's got composable components? So even if you're doing OO or something, it's still a very useful way of thinking about how to break down problems into smaller parts. I think is an extremely valuable way of kind of looking at the world. And so functional programming is just one way to kind of attune your mind to thinking that way. But once you start seeing it, you start seeing it everywhere. And then the next thing you'll be sucked into all the jargon, like you'll start talking about category theory and monoids and all that stuff.
Oh dear. So I think actually be really interesting to talk about it. So you work with F# Works consultancy, and it would be cool maybe to kind of discuss, how long you've been for a consultant, and how does it differ? How do you find being a consultant, having a consultant role as opposed to working in a single company, maybe with a single code base?
Yeah, I mean, I started being a independent contractor a couple of years ago, and it's okay for me because having a niche thing like F#, it's actually kind of good in a way, because if you want someone to do F# consulting, there's a limited number of people to choose from. So it's good. It works out quite well for me. Although, funny enough, I actually just came off doing a Python consulting job of all things. So that was fine too. So I'm not like strictly just F#, but I'll do any kind of job if it's interesting. There's I personally, I mean, I've enjoyed working in companies. I've worked in all sorts of companies, from kind of startups to big government things. And if the problems are interesting, that's fine. If the people are good to work with, that's good too. But I've also found some of my most stressful stuff working in companies too, and literally going crazy, and that's not good.
Well, it's harder to change, and it's, I suppose, adoption of things and stuff, as opposed to, in a consulting role. And if you specify, if you're interested in a certain thing and you want another problem, consulting's great because you get to see different places and different problems.
Yeah, I mean, the nice thing about consulting is it's a sort of take it or leave it thing. And in some sense, like if you don't like, I deliver something and hopefully it solves your problem. And if you throw it later, it's like, well, okay, I don't feel bad about it. It's not my fault. If I'm working at a company, I tend to get very attached to the kind of long-term thing of the company. And so that's the pro and the con. The advantage of working at a company is you can see something develop over a series of years, and you can start a project and then, you can nurture it, and like 5 years later it does, and you can see a lot of value being given to the business when something works well. So, I mean, that is one of the frustrating things about consulting is you tend to be more in and out. But the downside of, the flip side, of course, is that when you're working in a company, sometimes it's very hard to affect change. And I've realized that I think different people, again, people have different personalities. Some people like to fight for change and they sort of enjoy it. Personally, I kind of get stressed out by that, so I don't really enjoy doing that. And for me, what works is even more than consulting is doing publishing and being an author and training and stuff, because it's a one way. Basically, it's like, here's my blog, here's my book. I hope you find it useful. If you don't find it useful, sorry, I don't feel guilty. I don't feel like I have to apologize to people that it didn't do everything they want. I don't really have to respond. It's much more, my way or the highway, which is it's a terrible thing to say, but.
Well, no, because it allows you to shape your future of what you want to do, and it's kind of a lot less stressful and a lot less kind of going against the grain of what other people may want. You can kind of say, this is what I've got, and it is a take it or leave it approach, which as opposed to you've got to use this, or it's a conflict.
Yeah, and it's just my way of looking at it. And if you find that useful, that's great. And if you don't find that useful, that's fine too. And it's a much more hands-off thing. I don't have to sort of get emotionally involved when I'm working in a business, and I've been working there a while, I do tend to get quite passionate about things, and sometimes that's hard because especially big businesses don't find it hard to change. And also there's often a conflict between my logical model, my management not that I have a management background, but I've seen a lot of management things happen, and I can understand why managers do certain things which annoy programmers. For example, if you're a startup and you've got something that works, there's no point redesigning everything. It's okay. Building up lots of technical debt, for example, is very common at startups, and I can totally understand why they do that. They just don't have time.
They've got to try and find the product first, and then they can go back if they've got something that's going to solve something. It's a very different mindset. That code may not be around in a year because you won't have any funding and it's gone. So it's a race more than a marathon.
I mean, Facebook, wrote everything in PHP, and they're very successful, and now they're having problems with PHP, and they're using Haskell and OCaml or whatever it is. But I mean, if they'd written the very first thing of Facebook and Haskell, it might not have been successful. And so, there's a lot to be said for getting out of the door, even if it's buggy, even if it's not a very nice design, because it's, once it's making money is more important than having clean code. So, I mean, that's from my management hat on. From my programmer hat on, it gives me the shivers just looking at some of the code that's been shipped. So, I can understand sort of both points of view. It's a lot of internal conflict mentally between knowing, what's the right thing from one point of view versus what's the right thing from another point of view. And so that's probably why I'm not a very good manager, and I'd be very unhappy if I was in a management role.
Well, it's interesting because it's that whole tying yourself to a framework and things, and the whole Uncle Bob thing. Your structure of your application shouldn't look like a Rails application and things, or these kind of CRUD systems and very like a lot of frameworks go around this quick, rapid development lifecycle stuff. And you can understand that in the early time because, as you say, you're trying to get things out. You want to see if something sticks. And then you can go back and kind of hash out your domain because you don't really know your domain yet. You don't really know the problem you're trying to solve.
I used to do a lot of stuff with Visual Basic, and I used to do a lot of stuff with pre-Fox Pro. There was a bunch of kind of visual database languages. There was Paradox, and there was another one I can't remember what it was called. But they were great. I mean, you could literally knock together a UI in a few hours and connect it and complete with a database. I mean, they'd all be completely connected. So for CRUD apps, they were fantastic. By designing the screen, you'd be designing the database schema at the same time. And I mean, from a kind of big picture point of view, that's a terrible thing. But from getting something out the door quickly, they're awesome. And I think to some extent, we sort of lost that. I mean, it's kind of sad for me that you can't just build a web page out of some HTML. You now need to understand CSS. You have a JavaScript framework and all that stuff, which is a shame. This whole thing of knocking together. I do think there's definitely a role there's a lot of different kinds of programming around. I mean, sometimes you're programming the space shuttle, but sometimes you're hacking together, some brochureware for a small business, and you don't need to have the same kinds of programming processes for those different kinds of things. If you're knocking together a thing for a small business, just knocking together something in a few hours, that could be fantastically valuable. And so if you make it in PHP or you make it in Visual Basic, fine, that's great. There's value. It's valuable.
It's the transition, isn't it, though? It's when code goes from being just a hack thing together to being something that you maintain, and then you have to adapt it on. And that's when you have to decide, do you carry on with the path of what it's like, or do you then have to do a rewrite and things like that? And I think that's where the friction happens, where people are like, no, we've got to do it right first time. Or as opposed to, no, we can go back and just change the whole thing.
Yeah, I mean, that is a problem. And I mean, having had to maintain very gnarly Visual Basic apps, I can have a lot of sympathy. I don't know that there's a right answer to that.
It is very much context specific, isn't it? And kind of where, is it a kind of leave it or kind of slowly adapt on it? Because this is the trouble with things like WordPress. Anyone can set up a WordPress, easily set up something, and someone very novice can set it up, add a couple of extensions, and then you'll find, and this is a very typical use case, people will find like, oh, I want you to do X with WordPress, and they can't do that simply because there's no extension for it. So you then end up having to write your own things for it, or your own, I mean, this happens in any kind of like big application like that. Yeah, you get into this problem now where it's like, this problem you're trying to solve now would be easier if we rewrote this or had it in, we mapped it to domain, we looked at it from a point of view where we're not tied to something such as WordPress or a framework, but you started off that way, and it's that slow progression. But I think that's a client, maybe, again, it's the management client problem of trying to decide where that point is where you say rewrite.
Yeah, I mean, and I think this goes back to the whole thing of composition. If you had built things out of Lego, and you want another kind of piece of Lego, you want a motor in there, you can just like pull apart some of it and stick another bit in, and it will still sort of fit because because each piece is completely independent. And what makes something like WordPress really painful is that, I mean, actually WordPress is pretty good by most application standard. At least it has a plugin model, but the systems are not designed to be composable, and so I think you can sort of get the best of both worlds, where you can build little tiny things from a bunch of little building blocks, and then as the thing gets bigger and bigger, you can keep the same model and just make the building blocks more and more sophisticated. And going all the way back to the beginning example of Unix, the Unix components, which you connect together using piping, you can build some pretty complicated things using the standard Unix components. It's pretty amazing what you can do. Though I think where they begin to fall down is not the components' fault; it's the fact that using text as the interface, the universal interface is text. That sort of falls down. But I haven't really played with PowerShell, but PowerShell doesn't use as an object-oriented model, and I think you can do some pretty amazing things in PowerShell as well. So.
But it's interesting actually, because I remember in your talk you were saying, one of the things I think it was pinched from Wikipedia, about Unix is the idea that you don't rewrite, you write something new, and that's an interesting philosophy.
I think that's a very important. I mean, and what's interesting is that a lot of these things go back 40, 50 years. We think we're so clever for coming up with, dependency injection and composition and stuff. It's like people have been aware of this. People weren't stupid, 40 years ago. People thought about this stuff, and the idea of building things out of smaller pieces, the idea of building blocks and whatnot. But yes, the idea that you don't if you want to change the logic, rather than contorting the logic of one component and ending up with horrible conditional logic, well, if it's this kind of thing, do this kind of thing, do that. No, you just build another piece that does the new kind of thing, and then you glue those pieces together. You're a lot less likely to have bugs if you don't alter any code. If you treat your code as immutable, just like you treat data structures as immutable, it's kind of hard to introduce new bugs.
It's a very interesting mindset, isn't it, actually, to think of that, where, a code base is shipped and then to change it, you would have to write something new. And it kind of revolves around the single responsibility thing, where that's the responsibility it's solving. If you're trying to change it, you may be adding in extra responsibility. Exactly.
And I mean, and funny enough, this goes, one of the reasons why people like microservices, the same kind of thing. If your microservice is like, 300 or 400 lines of code, and you want to rewrite it, you literally throw it away and write a new microservice. You don't try and edit it.
It's such a kind of low cost hanging fruit, isn't it? It's not something you can just, it's easily torn out because it's only 400 lines of code. How long will that take to rewrite?
Yeah, exactly. And so, I mean, again, having lots of small components that fit together is a good idea. I think it's whether you call it microservices, whether you call it Unix pipeline, whether you call it Brio, whatever.
But you can do it, because that was something you were mentioning last episode, was, that you can do this in a monolith. You design, DDD can be done well in a monolith. You can do through namespace segregation and stuff. All these things can be done in just a monolith. You don't have to do the physical separation, which a lot of people think is mandatory to actually get around this. That's just kind of enforcing the rule, as opposed to, your mindset, you can enforce it.
Absolutely. If you do everything through interfaces, I mean, the classic OO thing, you do things through interfaces, you can rewrite the thing behind, you can change the implementation. Yeah, I mean, that's the theory. It's for some reason, I think it's because you're allowed to, what you're forced to do and what you're allowed to do. You're not forced to do that. You're not forced to have an interface for everything.
And there's always an escape hatch that's kind of an implicit escape hatch all the time with these things, I suppose.
Yeah, and in functional, again, one of the things about functional programming is it pretty much forces you to have interfaces, because every function parameter is actually defining an interface. So in an OO model, if I have a class that I'm passing in, if I want to say, actually, I really want to do it slightly differently, I have to make an effort to define an interface. And I have to decide, I have to think. And it's like halfway through the code, it's like, well, I don't really want to think. Let me just add this extra method to this class and just make this massive class, that does everything. In functional programming, the type is the interface. If I have a type, a function that turns apples into bananas or whatever, that is an interface. Any function that turns apples into bananas will fit, and so I don't have to define a special interface in order to swap out the implementation.
Absolutely. And it's been interesting, this whole talk, the whole discussion we've just had, a lot of these points kind of were brought up in a certain keynote that was done in ClojureConf in late 2017 by Rich Hickey, creator of Clojure, obviously. And it's this whole static versus dynamic typing, I would say a debate, but really, he kind of he wasn't attacking. I don't think he was attacking. I just think he was seeing it from his perspective of what he felt. And obviously Clojure is a very much kind of his opinion on things, and he wanted to solve a problem, and that's the way he solved that problem. And he saw from the languages that he was using at the time, that's how he wanted to go about doing it. I was just wondering, it'd be great to get your thoughts on it and kind of how you perceive it, how you perceive like his discussion on it, and also the backlash, or more like the kind of, flame wars that have happened since because of it.
Yeah, I mean, I have a lot of sympathy. I have a lot of respect for Rich Hickey, and I also have a lot of sympathy for dynamic people who develop in dynamic languages, because, I have spent a lot of time, probably 2/3 of my programming career I've spent in dynamic languages. A lot of Smalltalk, a lot of Python, a little bit of PHP and so on. And then, C# and now F#. I can really understand where he's coming from. I think dynamic languages, especially if they're very highly iterative languages like Smalltalk, which is an absolutely fantastic language. It's not just the language; it's the environment, and it's the way that the way that you do things. I think which Hickey was getting at is that the kinds of problems which developers need to solve, the kinds of problems which are solved by having a static type system is a very small part of that. And he's concerned when you're working with a business domain, the real world is complicated and the real world has weird stuff in it. Yeah, things change and you want flexibility. One of the things about types languages is that types cause coupling. So if I have one function that spits out, cherries, another function that inputs cherries, I can't, I need to have cherries around. I can't just have part of a cherry. If I have
something that looks like a cherry but has extra stuff, like cherry with extra, you wouldn't be able to pass that in.
Exactly, and I wouldn't be able to pass in just the cherry stone or the stalk or the whatever it is. So there's coupling. Types do induce coupling between. I guess in a sense, types are anti-modular because they are kind of global. I wouldn't say they're a global variable, but they do.
But aren't they that? Isn't that their strength? I think that's where I kind of go. Part of it is the fact that it's defining this very strict thing. It's a very strange world.
It's a contract. It's a contract between things, and so the good thing about having a contract is that it's a very strict contract, and if you break the contract, you know straight away. The compiler is giving you a compile time guarantee that you've broken the contract or you haven't broken the contract. If you don't have types, you have a lot more flexibility. Now, so the question is, what are the problems that we try and solve as developers? And Rich Hickey's point of view is that that static typing does not really address. It's addressing the problem of correctness. And does it meet the requirements? Does this piece of code meet the requirements? You say, I want this input, I want this output. There are other ways of doing correctness checking without using static types. So like closure spec, for example. And it may be that correctness is not the most important thing in a program. It may be, there's a classic, this goes back to management theory. Peter Drucker, a well-known management writer, had, made a very important distinction between effectiveness and efficiency. So efficiency is how well does your car engine work? But effectiveness is, are you driving in the right direction? And there's no point if you have a super efficient engine if you're driving in the wrong direction. So it's much more important to be going in the wrong. It's better to go in the right direction on a bicycle than to go in the wrong direction in a Porsche. And so we spend a lot of time, I think, as developers focusing on efficiency. What's the best compiler? What's the fastest compiler? What's the best way of ensuring correctness? And I think his point is that we can get lost in that. And often what's more important is being effective, is actually going in the right direction. And static type systems, if you're trying to solve a business problem, they don't help us go in the right direction. That was sort of his point.
Yeah, and it's the inertia of a type system and how, it's beautiful when it compiles and understanding this beautiful correctness of it, but is it actually solving the problem? You don't know. It may compile, but it may be not solve, you say, the business problem, which we mentioned before.
I have a lot of sympathy with what he's talking about, and I think a lot of the static type people really misunderstood what he was talking about. I personally think that you can have both, and I think having a correctness is actually quite important, especially if you have a large code base. Trying to refactor, especially in enterprise development or any large code base, you're trying to refactor it when you're coming back, 5 years later. I think types are really, really important. I think actually having an explicit contract is actually really good, and I think types are a great way of enforcing contracts, because the compiler can do it for you. You don't need to rely on people using something like spec to, you can make mistakes, and with a compiler doesn't make a mistake in the same way. So I do think you can get sort of the best of both worlds, and that's why when I focus, when I talk about functional programming, I talk about things like domain-driven design, and I talk about using types as to represent to document the design. That's why I'm not big on purity above all things, and some of the other things that people talk about with the kind of mathematical concepts behind. I'm not going to really force you to learn category theory.
You're going to show the bits that actually matter and work in a real life use case.
Yeah, you see, I think that programming is actually a human discipline. It's not a mathematical discipline, and this is where,
which is what he got in his keynote, which was quite good as well. You know, what he envisages it. Programming is not a mathematical thing.
Exactly, and I think that's a difference between. Again, that's one of the. It's a different paradigm. I think people are talking past each other. There are people who believe that programming is a mathematical activity, and if we only used mathematical techniques, our programs would be better. And to some extent, that's true. I mean, it is true that we can learn a lot from the mathematical thinking about. We're very, very, very sloppy in our code, and especially things like security holes and stuff. Taking things seriously and having techniques which really do work, I think mathematics can offer a lot. But I also have another foot. I mean, I have a lot of sympathy with the programming as a human activity to solve human problems, and it's always going to be, anytime there's people involved, it's going to be a complex system. I mean, there are some areas of programming which are not people-centric. So, for example, if I'm designing a database, that's pretty much like the requirements are very clear. I don't really care what people say because the requirements are, I need to have transactional this, and I need to have integrity here. And if I'm Google and I'm designing the search algorithm or the big table algorithm or whatever, that's very, very mathematical.
Yeah, you can have tight algorithms that require, and are very strict in what they are.
Right, but if I'm designing something which is
like a GUI or whatever, kind of thing.
And it's kind of interesting to see that Google actually is pretty rubbish at designing. I mean, it's interesting to compare Google and Facebook because Google has a very, I wouldn't say they're mathematical, but they have this very kind of academic approach, or certainly they did at the beginning, of solving things, and they've done a fantastic job at solving certain kinds of problems. But they've done a terrible job at in terms of their user-friendly programs. Google Plus and all these things have been disasters.
Wave.
Yeah, Wave and stuff. I mean, Facebook, I'm sure the early code at Facebook was absolutely rubbish, and it was completely unsound, and it was full of bugs and stuff. But it solved a problem that people really liked, and Facebook, as a result, has been very successful. So it is interesting. I don't think there's a one size fits all. I think if there's people involved, then the programming using mathematical approaches is never going to be enough.
Because have you used Clojure and Lisp dialects in the past?
It's on my list of things. I've kind of browsed it. I haven't ever done anything serious with it. But no, I mean, I do think Clojure seems to me like the kind of language I would like because, again, it's opinionated.
Yes, that's what I was going to say.
It's like this is the way you do things. This is our philosophy. There's a philosophy of how you do things. And I mean, I think that's good because once you learn it, I imagine if you look at a decent code base in Clojure, you pretty much understand mostly how it works because everyone's doing things roughly the same way.
And it's boiling it down to a map. It's all about maps, and the idea that having 100 functions for one data type is better than having 10 functions for 10 different data types. Doing one thing, doing it well, and reusing that.
Yeah, I mean, and that's something you do. If all your data types are maps or dictionaries, that's great. I mean, funnily enough, the early version of Python before it got object-oriented was exactly the same. Everything was just basically a map. And in Smalltalk, everything's basically a map, everything. And so, and Lua, I think, is very much similar that way.
PHP as well, actually. The idea of associative array, I mean, even an array really is just under the hood, just a map.
Yeah, exactly. So, I mean, in a funny sort of way, having a consistent philosophy, I think PHP is a bit of a mishmash, but languages where there are definitely a philosophy of doing things, I like those languages because, again, learning the language is going to change the way I think. If it's learning Clojure is going to be very different from learning Java. It's definitely going to change the way you think about programming, and I think that's a good thing. I think as a developer, and you want to kind of expand your personal abilities or your personal growth, learning languages like that is very good, even if you don't actually use them on a day-to-day basis.
No, that's awesome. And just thinking that we've hit over the hour mark, so it'd be really cool actually maybe just to finish off with kind of just like a platform for you. Like, is there any interesting topics that you've currently been exploring or reading about?
There's not really right now. In general though, I tend to think the most interesting thing for a developer to do if you want to learn new stuff is to look at things outside non-technical stuff. So look at management theory, look at psychology of teams, look at user interface stuff, look at a lot of this stuff, because I think this helps you be a better developer, because it exposes you to a whole world of things outside of technical stuff, and it also helps you interact with non-techie people. Understanding how teams work, understanding the psychology of how different people work. Like family therapy, it's interesting. Some people really like those books on family therapy, and it's like, well, why is that relevant to programming? Well, it turns out that a lot of the things that show up in a family show up in development teams as well. Somebody arguing, having vicious fights over stupid things. The daddy figure and the mommy figure and all this stuff. So it's kind of interesting. And I personally like to read people who, and for example, the whole thing of design patterns that came from architecture. So expanding your horizons outside just the techie stuff, I think is definitely a good thing in general.
It's interesting because, like, from an outside where I perceive you, you're very much, you've always got a math background, and you would assume that you would be very much into that kind of academia stuff. But then obviously, you're very interested in the human aspect as well, which blend is just amazing, to kind of have. But I'm just interested, do you do a lot of research still in academia circles with maths and stuff, or you mainly looking into this for psychology?
No. I got enough maths that I can read stuff, but I'm not, to be honest, I find it fascinating, but when I went to college, I realized there were people who were so much cleverer than me. There are some people who really are sort of geniuses, and I couldn't possibly compete with those kinds of people. It's like they're on a whole different level. So, I find it interesting.
Well, you provide a valuable service to dilute it down into something that, us mere mortals can understand. So I highly appreciate it.
Yeah, well, going back to one particular book, there was a book called Crossing the Chasm, which came out in the 90s, and it in turn was kind of a popularization of a theory called the diffusion of innovations. And that book talked about that was the one that sort of introduced the idea of early adopters and late adopters and mainstream and so on. And the chasm there is the bridge between the early adopters and the late adopters, the people who will just use new technology for the hell of it because it's cool, and the people who actually want to get some value out of it and are not going to just do something because it's cool. And there's a chasm, there's a gap between the two. And the whole book was, how do you cross that chasm? How do you make stuff useful to people? And I sort of see that's where my role is, to basically be a bridge across that chasm, is to try and take ideas which I think are important but not necessarily mainstream, and help make them mainstream by explaining them to people in a way that's not intimidating, and basically it should be easy to understand.
Well, I'm going to say personally, you do that very well, and I'm sure a lot of other people would say the same.
Well, thanks very much.
Awesome. Well, I think, audience, it's been another great episode, and we'll speak to you again next week. Goodbye.
You've been listening to 3 Devs and a Maybe. You can contact us at contact@3devsandamaybe.com, or follow us on Twitter at 3 Devs and a Maybe.